Hey, pup.
Hey, Rack.
Hello.
Fixing the bugs. The algorithms that we published last summer and last fall worked for a lot of small test cases. And we knew that they did not work for all cases. But we thought that all remaining fixes would be trivial. We were so wrong. We have now fixed all of the bugs that we have found. Some of the bugs expose the subtleties of the algorithm, which is why we're describing them here. For example, some bugs clarified the difference between Euclidean and fractal thinking. The equation butterflies remain essentially the same, however the dynamic programming rules changed a bit. The solution butterflies changed a lot. They still embody the intersections of equation butterflies, however they have become spines that are now truly fractal. Before we get to the bug fixes, we have a note on complexity. Our current algorithm is quasi-polynomial. We can think of it as approximately n to the log n, though constants may make it a bit worse. In earlier videos in this series, we claimed that our algorithm was polynomial because we thought we had optimizations. However, they did not pan out. Our algorithm is quasi-polynomial, or specifically, big O of exp of c times log of b squared, where b is the number of bits in the product. The general number field sieve, which was the previous best algorithm for factoring, is sub-exponential, or specifically, big O of exp of c times b to the cubed root and log of b raised to the 2/3, where b is the number of bits in the product. Our algorithm for consistency improves the complexity of factoring, as well as various combinatorial problems, specifically critter-complete problems, though it remains impractical. Here we cover fixes to the equation butterflies. First, in equation butterflies, we did not realize that parent constraints must be applied simultaneously. We came across this example while debugging. Based on the equations for computing box values, a equals c plus d divided by 2, and b equals c minus d divided by 2. Originally, we had treated the values for a and b separately. So, for example, if C must be in the set -2, -1, 0, 1, and 2, and D must be in the set -2, -1, 0, 1, and 2, then for all values of C, there is a D that will produce the value A equals 0. And for all values of C, there is a D that will produce the value B equals 0. So, for example, if C equals -1 and D equals 1, then A equals 0. Likewise, if C equals 2 and D equals 2, then B equals 0. So all values of C and all values of D work independently. However, if we require that the values for C and D produce values for A and B at the same time, then only one pair works. So let's take the pair C equals -1 and D equals 1. A equals -1 plus 1 divided by 2, which equals 0. That works. However, B would be -1 minus a positive 1 divided by 2, which equals -1. That fails. So -1 and 1 do not simultaneously produce a valid A and a valid B. In this case, the only valid pairs are C equals 0 and D equals 0. Our second problem was total sums. Originally, we said that the partial sums in the top tier, or the total sums, must equal either 0 or n for binary constraints. We ignored the route by which they got there. This is an example of the butterfly for the constraint vector 1, 0, 1, 0. Taking the fast Hadamard transform gives us 2, 2, 0, 0. The tuples in the bottom row show each Hadamard value with its corresponding partial sum value. The partial sum value comes from multiplying the Hadamard value times the corresponding element from the fast Fourier transform of the constraint vector. The middle tier shows all tuples that derive from valid tuples in the bottom tier, and the top tier shows all tuples that derive from valid tuples in the middle tier. Now, if we require that the total sum equals 0, then only the tuples in black in the top tier are valid, because all of the other tuples have a total sum that is not 0. If we remove all tuples in the middle tier that do not contribute to valid tuples in the top tier, then the ones marked in red will be removed. And likewise in the bottom tier, if we remove all tuples that do not contribute to valid tuples in the middle tier, then we will remove the ones marked in red. This is the butterfly for the total sum equals 4. The tuples are the same tuples, but in the top tier, we only allow tuples that have a total sum of 4 to remain valid. So we mark a different set in red as invalid. And in the middle tier, if we remove all tuples that do not contribute to valid tuples in the top tier, then we will remove the ones marked in red, and likewise in the bottom tier. Here's where the leap of imagination needs to occur. The tuple 2, 0, marked in green, in the bottom row, third node, is valid for the total sum equals 4, but is invalid for the total sum equals 0. If the dynamic programming were allowed to mix tuples from the butterflies for total sum equals 0 and total sum equals 4, then it could combine the tuple 2, 4 from node 0 with the tuple 2, 0 from node 3 to create the tuple 2, 4 in the next tier up. The tuple 2, 4 would be marked as valid, even though it is invalid, as shown in green. Butterflies of size 4 are too small to show the whole problem. Larger butterflies that mix the total sums enable Hadamard vectors that should be invalid to appear valid. To extend that bug, we confuse the meaning of ors within equation butterflies. We had thought that we could simply union the equation butterflies for the total sums of 0 and n. The butterflies already handled the ors of the partial sums. In other words, the butterflies already handled all of the different ways that Hadamard vectors could sum to the specific total of 0 or n. And we thought the equation butterflies could simply union the total sums for 0 and n. However, we eventually realized that each constraint must have a separate equation butterfly for when the total sum equals 0 and for when the total sum equals n. Fixes for solution spines. This section is a bit involved, so we will go through these steps piece by piece. We first describe the goals that solution spines solve. Then we'll discuss solution triples using Hadamards and addresses. We will compare additive or Euclidean states with multiplicative or fractal states. We will discuss representing solution butterflies as solution spines, and we will describe extracting as a search through fractal space. Intuition. We start with the bunch of constraints C, where C is the bunch C0, C1, and so on through Cn-1. Each constraint Ci identifies 2 bits, j and k, that may not both be true at the same time. The solution S will come from selecting a Hadamard vector from the intersection of the constraints. So this equation S equals sigma of pi of C0 intersect pi of C1 intersect pi of Cn-1 expresses what we want to happen. We're going to project something from each constraint, we're going to intersect those results together, and then we're going to select a Hadamard vector from the final result. Note that this equation solves consistency. Notes on constraints. Each constraint C represents either 1 or 2 total sums. The total sum is in the set 0, or the total sum is in the set 0, n. Each constraint C must separate the equation butterflies for the total sum equals 0 and the total sum equals n if the constraint allows both total sums. Notes about pi of C. Intuitively, pi of C projects the Hadamard structure of constraint C. The Hadamard structure is a fractal. Pi of C must union the equation butterflies within the constraint C for total sum equals 0 and total sum equals n if the constraint allows both. Unfortunately, unions are the hard part of this whole algorithm because unions have sabotaged many potential solutions. Notes about solution spines. We call the result of pi of C a solution spine. Solution spines are like butterflies, but are much smaller. The solution spines of the different constraints will get intersected together. Solution spines are fractals of addresses. Notes about sigma of S. Sigma selects one valid Hadamard vector from the solution spine if it exists. Sigma of S performs a fractal search This diagram shows how we now prefer to draw solution butterfly nodes. Leaf nodes will remain flat, as shown by the bottom tier. All parent nodes will be represented by two nested squares, as shown in the upper tier. The outer square is indexed by the domains of the children nodes. Note that three of the diagonals have the same order as the order of the domains in the lower nodes because they are added. The rightmost diagonal is reversed, going from 2 to -2 because it is subtracted. The inner square is indexed by the domain of the parent in the horizontal direction and by the alternate ways to produce those domain values in the vertical direction. Note that each column of the inner square has the same Hadamard value. Only the values in the inner square remain valid at the next level. All of the values in red are out of range for the domain of either the left or the right parent. Consider the two numbers circled in red. On the right, the -1 lies outside of the domain of the parent, which is 0 to 2. On the left, the 1 is actually in the parent domain, except that it will be computed from the same pair of child Hadamard values as the -1 on the right. Solution triples. The first record here in blue shows our original design for solution triples. Each triple represents combining a left child Hadamard and a right child Hadamard to create a parent Hadamard. This failed because it did not capture the structure of the partial sums. The second triple here does work. Each triple represents combining a left child address and a right child address to create a parent address. This diagram shows three nodes from a solution butterfly, the left and right children as well as a parent. In this case, we'll assume it's the left parent and simply add the values. The left child has three different ways to produce a Hadamard value of 1. The right child has three different ways to produce a Hadamard value of 1. And so there are 9 different ways to produce the 1 in the upper right corner of the parent. Within equation butterflies, the partial sum values constrain which of these combinations are valid in the parent node. If we treat all of the 1's on the left as alike and all the 1's on the right as alike, then we cannot distinguish between valid and invalid combinations. Partial sums may impose the constraint that only the light green and the dark green paths to produce the 1 in the upper right-hand corner are allowed. All others are forbidden. So we need to represent this constraint. So we need a way to prevent this particular combination of a light green one from the left and the dark green one from the right combining together. The answer we came up with is to define solution triples in terms of addresses. An address simply combines the left and right child Hadamard values. In the left child node, the light green 1 comes from a 1 and a 1 on the next level down. The light blue 1 comes from a 2 and a 0 on the next level down. In the parent node, the black 1 comes from a 1 and a 1 on the next level down. And the address identifies exactly which cell in the child node the Hadamard value came from. The addresses are the true points of flexibility. In the parent node, saying that 1 and 1 can create 1 is ambiguous because it doesn't tell us which combinations of the child values that create 1 are valid. This is shown in black. The parent value of 1, 1 in green is a combination of a 1, 1 on the left child and a 0 minus 2 on the right child. And the 1, 1 in blue is a combination of the 2, 0 on the left child and the 1 minus 1 on the right child. Here are the constructors for solution triples. The first constructor is for leaves. It takes a Hadamard value and converts it into a parent address that works equally for both left and right nodes. The second constructor is for parents. It takes the left and right child addresses and constructs the parent address. The Hadamard function returns an actual Hadamard value. It first splits the parent address into left and right Hadamard values, and then either adds or subtracts them and divides by 2, depending on whether this is a left or right node. Euclidean versus fractal shapes. The nodes in each tier have domain sizes that are powers of 2 plus 1. So they are the series 2, 3, 5, 9, and so on, as shown by the top row. When we add the nodes together in a Euclidean fashion, the state grows arithmetically, as shown by the middle row. Equation butterflies grow like this. When we multiply the nodes together in a fractal fashion, the state grows geometrically, as shown by the bottom row. 2 is a line, 2 times 3 is a rectangle, 2 times 3 times 5 is a cuboid, and 2 times 3 times 5 times 9 is a hypercuboid, and so on for dimensions beyond 4. Solution spines grow like this. This diagram depicts a solution butterfly, except that states are multiplied together along the vertical arrows. The thing is that we do not need to represent everything related to this solution butterfly in order to represent the valid Hadamard vectors. We only need to represent the spine tree. The spine tree is all of the nodes that are associated with the node tier 0, term 0, as shown by the light blue arrows. By associating the spine with tier 0, term 0, child Hadamard values are always added together, which simplifies the logic. Spines represent the same information as complete butterflies. If a full butterfly exists that represents a Hadamard vector, then a spine exists because the spine is simply part of that full butterfly and that spine can represent that particular vector. If a spine exists that represents a particular Hadamard vector, then the full butterfly also exists because the whole butterfly can be reconstructed from a Hadamard vector. We know that a spine exists if and only if a full butterfly exists, because if A implies B and B implies A, then A equals B. The path from node A to node I, as shown in light green, is part of the spine. The path nodes are A, C, D, G, and I. The sibling nodes are B, E, F, and K. The path from node A to node J, as shown in light blue, is part of the spine. The path nodes are A, C, D, F, and J. The sibling nodes are B, E, G, and H. This diagram combines both paths. Consider a Hadamard vector where I has one value, say 5, and j has another value, say -2. If I and j are in the same Hadamard vector, then the Hadamard values assigned to A, C, and D must be the same. The values assigned to F and G may differ as long as they are consistent with the values of A, C, D, I, and J. There are two obvious representations for spines. The first entwines the paths into a binary tree. This would be a binary tree fractal of path fractals, so there are two fractals. The advantage is that this uses ON less space, but is much harder to think about. We could also separate paths across an array, which would be an array of path fractals, one for each leaf. This uses ON more space, but is much easier to think about. The code below will use this second representation. This is the class solution spine. Each spine object contains an array of paths, one for each leaf. The constructor takes an equation butterfly and extracts one path fractal for each leaf. The pi, or project function, converts constraints into solution spines. If the constraint is unary, it simply creates a spine for the constraint with the total sum equals 0. If the constraint is binary, it creates a spine for the total sum equals 0 and another spine for the total sum equals n, and unions the two spines together. The function spine takes a constraint and a total sum. It first creates an equation butterfly for that constraint and total sum, and then it converts the equation butterfly into a solution spine. The two-path function extracts a specific path from an equation butterfly. This function has been derecursed to show the shape, however the actual implementation is recursive. First, the function creates 4 temporary variables and 1 return variable. The array's path nodes and sibling nodes simplify the logic. The array's path pairs and sibling pairs will be filled in by the logic below. They will be used to construct a series of addresses that will be used to identify a specific cell in the solution path fractal. Solution path identifies which sequences of addresses along a path are valid. Solution path will be the returned fractal structure. The outermost for loop goes through each equation pair in the leaf node. The next for loop in light blue processes all of the equation pairs in the sibling of the leaf node and computes the parent equation pair. If the parent equation pair is valid, then it continues. The next for loop in medium blue processes all of the equation pairs of the sibling of the parent node. It creates a grandparent equation pair. If that grandparent equation pair is valid, it continues, and so on. The last for loop in dark blue processes all of the equation pairs in the sibling of the second to the top node, in the second to the last great-great-grandparent node. It creates a great-great-great-grandparent equation pair. If that great-great-great-grandparent equation pair is valid, it continues. If the sequence of spine pairs reaches the top tier, then the innermost line of code will assign true to the corresponding state in the path fractal. Finally, it returns the solution. These diagrams illustrate the two-path function. The outermost loop enumerates all of the equation pairs in the leaf of the equation path. The next loop, in light blue, enumerates all of the siblings of the leaf of the equation path. Those two child equation pairs identify exactly one parent equation pair, as well as one address in the solution path node. The next loop, in medium blue, enumerates all of the equation pairs in the sibling of the parent node. The parent equation pair, as well as its sibling equation pair, identify exactly one grandparent equation pair, as well as one address in the parent node of the solution path. The innermost loop in dark blue enumerates all of the siblings of the great-great-grandparent one step below the last node. Together, the equation pair in the equation path, combined with the sibling pair, identify exactly one equation pair in the root node, as well as one address in the root of the solution path. Every time the loops get to the innermost line of code, the function will assign true to the specific cell in the solution path identified by the addresses. The parent function creates a parent equation pair from a left child and a right child if it is possible. Otherwise, it returns null. First, it checks whether the left child and right child could create a valid parent. If so, it creates the parent. Then it determines whether the parent equation pair is actually in the parent node. If so, it returns the parent equation pair. If anything goes wrong, it returns null. This is the select or sigma function. We defined it recursively to begin with. It does a top-down fractal search through the binary tree-shaped spine. The function first creates an array of Hadamards to store the answer, if one is found. It then calls helper to recursively search through the space. And finally, depending on the result of the search, it returns the Hadamard vector or a null. The helper function does the main work. It takes a tier and a term, which identifies the node to process. It takes a parent address, which must be matched, and it takes the resulting list of Hadamards to fill in. The outer loop considers all solution triples within the domain. If the parent address is null, then it will match any solution triple. Otherwise, it must match the solution triple's parent address exactly. Within the loop, there are two main cases. If the tier is the bottom tier, or log n, then the function records the Hadamard value and returns true. The function found a Hadamard value for this particular node. Otherwise, we compute left term, left address, and right address as shorthands for the recursion. The real work is done by calling the helper recursively on the left child and on the right child. This is the fractal search. If both children have been filled in properly, it returns true. Otherwise, the loop continues with the next solution triple. If no solution triple leads to filling in all of the Hadamard values below this node, then the function returns false. We have now fixed all of the bugs that we know about. But we don't know what we don't know. and there still may be bugs. Please be skeptical of our results until everything works. We expect the code to be up on GitHub in early April.